I'm going to skip the first section in chapter 3, section 3.1. Just making sure it's the same in this newer version of your textbook. Yep. Section 3.1 basically crams in every ancient culture's study of astronomy except for the Greeks and shoves it into one section, which is really, each culture could have their own textbook. You could spend a whole semester talking about ancient Chinese astronomy. You could spend a whole semester talking about Native American astronomy. So putting it all in one section just doesn't do it justice. So we're just going to go ahead and skip ancient astronomy, and we're going to just move up to the Greek version. Have a cartoon. I think it's cute. So section 2 is ancient Greek astronomy. And we're going to focus on ancient Greeks because they have records that have survived to this day, so we know who did what. It's easier to talk about it. We have dates. But also because the ancient Greeks they had a philosophy that they would use what they saw and try to explain what they saw without invoking supernatural explanations. And then they would also use math to try to see if they could find a formula for it. Okay, so we would call this the basic roots of our modern science. So let's go way back to 500 BC. In the 500 BC era, the Greeks believed that the universe was geocentric. Basically, Earth is at the center of the universe, and everything goes around us. So, Earth is at the center. The moon, the sun, the stars, the planets, they are all moving around us on perfect circles. By 500 BC, they knew the Earth was round. They just knew the Earth was round. The people who believe or have heard that Columbus thought the Earth was flat in 1492 when he sailed the ocean blue, it's a rumor that refuses to die. They knew the Earth was round way before Christopher Columbus. Move up to 250 BC. We have records from this time that show that the heliocentric model had been suggested, so sun-centered. The sun is the center. They were suggesting it. Nobody, switched, geocentric stuck around as the prevailing model. But Copernicus was not the first person to suggest it. In 250 BC, Aristophanes calculated the Earth's circumference to within 2% error. Aristophanes calculated the Earth's circumference, so he knew it was round, to 2% error. That 2% is a little bit questionable because we had to convert from his units to our units, and the exact conversion is a little fuzzy, but let's give him some credit. We'll go and say that 2% error, but just understand that it might be a little bit more than that if our unit conversion was a little bit wrong. Jump up 150 AD to Ptolemy. Ptolemy, we're going to say, had the best and most accurate geocentric model ever. Okay. Some things to realize about Ptolemy's model is it is geocentric. Everything is on perfect circles. But if you only used perfect circles, I'm going to click back here. Notice here there's circles, 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 and you can kind of imagine the planets going around in the circles. It didn't reproduce what you saw in the sky. In order to explain retrograde motion, you'd have to have these orbits, these circles, stop and go backwards at some point. And sometimes the planet moves a little bit faster across the sky and sometimes a little bit slower. So Ptolemy added epicycles. If you want, you can define epicircles as circles on circles or wheels on wheels. And Ptolemy, by using epicycles, his model could make accurate predictions of the sky for 1,500 years. So Where is Jupiter going to be in the sky in 5 years? In May. Ptolemy's model could tell you. When is Mars going to go through retrograde motion in a decade? Ptolemy's model could tell you, and it was correct. So people trusted this, and this is going to be the model that we're going to use for a long time in astronomy. It is odd. So let's take a look here at Jupiter. Jupiter has an orbit. The orbit is this larger circle. And Jupiter, the planet, isn't actually on the orbit. Jupiter is attached to this little wheel, and the wheel moves on the orbit. So Jupiter spins on this wheel while that wheel is moving along the orbit. It worked. Mercury and Venus, are never seen at night. They're only seen like right in the morning or right in the evening. So that's why they are attached to this line to the sun. If the sun is going to be moving around the sky, Venus and Mercury had to move with it. They could stray a little bit off to the left or right of the sun, so we could see it in the morning or evening, but you would never have them up at night or at midnight. Let's look at these epicycles a little bit more, these circles on circles, and how Ptolemy used them to describe retrograde motion. Right. So here is the epicycle. Here is the orbit, and when I press play, Mars in this case, because it's red, is going to move on one circle, which is moving on the larger circle. And the circles are invisible or imaginary, so what you would see is for a little bit of time, from here to here, Mars goes backwards. So that's the retrograde. So Ptolemy actually said that these epicycles are what caused the retrograde motion, and he timed all of these wheels perfectly. And even for more accuracy, sometimes he had an epicycle on an epicycle on an epicycle, which we didn't draw for you here just to keep it simple. And all of these wheels were timed. Your textbook likes to say that for the geocentric model, for these epicycles, the planet moves backwards in its orbit for retrograde motion. So right here, that is when the planet would move westward across the sky. And the planet is also moving in the opposite direction in the orbit. I don't like the way they say that the planet moves backwards across this, stops and moves backwards in its orbit, because it was always moving smoothly forward on its circles. So just be aware of that. So Ptolemy's model was accurate for a very long time, 1500 years, and it was accurate, so people trusted it. So many people in history have suggested a sun-centered model, but we have this really great geocentric model, Ptolemy's. It's still working. Let's just keep using it. Plus, we don't feel the Earth move. We don't really want to believe that the Earth is hurtling through space and we can't feel it. So people stuck with Ptolemy's model. So we're going to jump up here to the 1500s with Copernicus. By this time, people were still using Ptolemy's model all the way from 150 AD up until the 1500s. The Earth is the center of the universe, perfect circles and epicycles. Copernicus comes in and says, I don't like using these epicycles. The math is complicated. It would be much more elegant and simple to explain retrograde motion if the sun was the center of the solar system. So heliocentric. If the sun is the center, right, you get retrograde motion whenever one planet laps another. And so he put the sun at the center, and he put all of the planets around the sun on perfect circles. But perfect circles are not actually how our solar system works. We'll get into that in a little bit. So his model was not very accurate, at least not any more accurate than Ptolemy's was. So nobody really wanted to switch. It didn't feel right in their gut, and it wasn't any more accurate. So Copernicus didn't convince the world that the sun was the center of the solar system, but he did do a lot of math and geometry and figured out a lot of the basic stuff, and he tried to convince people that the sun was the center of the solar system. Eventually, Copernicus ended up adding epicycles, circles on circles, for the planets, just so that they could become more accurate. So he basically just put the sun at the center instead of the Earth, but his model got just as messy and complicated as Ptolemy's. So we're going to go forward in time, and the majority of people are still going to say the Earth is the center of the universe. Let's go to Tycho Brahe. Tycho Brahe got some money from royalty to do the best naked eye observations of the planets and stars' positions. And that was his life's work, was to measure the planets' positions and the stars' position every night. And he still holds the record for the best naked eye observations ever done. In a little while here, the telescope is going to be invented, and nobody's going to bother doing this with their naked eye anymore. So Tycho's main achievement was taking these great observations, marking out the planet's positions very, very accurately. Once you have good data, then you can try to fit the data and see what's causing it. Tycho took his amazing data and tried to figure out the solar system, tried to figure out the universe. And I'm just going to show you this figure here on the right just because I think it's hilarious. Tycho had his great data and decided to make a model, and nobody believed him. Nobody believed his model, and I can't say I blame them. Here's his model. Earth is at the center of the universe, at the center of the stars. The moon goes around Earth, and the sun goes around Earth. But every other planet orbited the sun while it was orbiting the Earth. So I imagine that Tycho was crushed. Nobody believed him. The rumor goes that he then said to his student, Kepler, please take my data, find the explanation of how the planets move in the sky, and make my data worthwhile, make my life worthwhile. Another story goes is that Kepler ended up killing Tycho and taking his data. The truth is probably somewhere in between the two stories. So let's move on from Tycho to Kepler. Kepler took Tycho's data and said, if the planets move on perfect circles, with the sun at the center, does Tycho's data work? Does it agree with a sun-centered model with perfect circles? And I would say that it worked. It worked really pretty good. You use the model and you make a prediction of where Jupiter should be in the sky in, I don't know, a year. And then you use Tycho's model and you say, where should the model put Jupiter? And you go out and you see if it's right. And Jupiter was off by the tiniest little bit of position. It was just off a little bit. In my classes, I like to have them have a penny, get a penny out of their pocket, hold the penny up at arm's length. You're holding the penny up at arm's length, and you're looking at the Lincoln side of the penny, and Lincoln's eyeball. So at arm's length, Lincoln's eyeball looks really small. The position of the planets was off by a Lincoln eyeball. If that was my work, I would have said, hey, look, that's great, good job. We did it. Perfect circles with the sun in the center. It works. Kepler becomes famous, and I think rightfully so, is because he said, we can do better. Even though I've been trained my whole life to believe that the heavens have to have perfect circular orbits, I think we can do better. Tycho's data should have done better than one Lincoln's eyeball. Right? So let's just follow the data. Let's try a different shape and see if it does any better. So he tried ellipses. So Kepler comes up with 3 laws of planetary motion in the sky, and we're going to go through all 3 about ellipses. So Kepler's first law: all planets orbit on an ellipse with the sun at one focus. So let's start off with what's a focus. Something I do on the board, but you can do it at home, is get a piece of string and tape the string down at one end and tape the string down at the other end, leaving some slack. Right, there's the slack in the string. So tape it down, tape it down. Where you put the tape for the string is called the focus. It's just a geometry term. Right? You use a pencil and you pull the slack out of the string. And then you drag the pencil around, keeping the string taut, and you will draw yourself an ellipse. And it works really great. Just try it. Okay? You have yourself an ellipse. So all planets orbit an ellipse with the sun at one focus. Pick one. Let's pick this one. So you could draw the sun right there on one focus. What's at the other focus? Empty space. Gravity doesn't need the other focus. I'm like, you need it with a string and a pencil, but gravity doesn't need it. Gravity only needs one of them. So draw the sun there if you want. So the sun would be here. The planet would move on this red curve, the ellipse, around the sun. If you go the shortest way across the ellipse, that's called your minor axis. If you go the long way across, it's called your major axis. We actually will end up needing the semi-major axis. So, semi-major axis. So what you can do is imagine the longest way across and cut it in half. Another way of looking at it is just pick the center, start there, and measure out to the distant edge. That's your semi-major axis. You would measure it in kilometers or miles or AU, astronomical units. So from the very center to the distant edge, that's your semi-major axis. We will need that later. Right. Let me play this one more time before we move on. Right. Kepler's second law. You could state these laws different ways. It's a matter of translation or personal preference. I have it up here the way I've found it best, after semesters of teaching. So Kepler's second law, the way I phrase it is, a planet moves faster when it is near the sun, sweeping out equal areas in equal times. So in this animation, we have the sun at a focus. We have a planet, let's call it Earth because it's blue, right? And the planet is going to go around the orbit, right? Ignore the sweeps for a second and just watch the speed of the planet as it goes around the sun. Slower, faster. Okay? Slingshots around. Slower and faster. So what the sweeps are is, it's basically the area that the line that connects the Earth and the Sun sweeps out over a certain amount of time. So if you let the Earth travel for 1 month, it would sweep out this green triangle, which has a certain area. And I'm even rounding by saying triangle. It's more of a wedge, a pi wedge. And it's going slow, so it's going to be a skinny wedge. Skinny and long wedge. If you go to any other part of the orbit, and again let the planet move for 1 month, the same amount of time, that line is going to sweep out a pi wedge. That has to be the same area. That's just how Kepler calculated it and phrased it. Right? What the implication is that the planet moves faster when it's closer to the sun. That's the implication. That's what you might find much more tangible and easier to remember. I like to also point out that notice that as it starts out at what we call aphelion, farthest away from the sun, it's going slowest. And then as it falls closer to the sun, the gravity is pulling the planet towards and closer to the sun, so it's going to pick up speed. And at perihelion, the closest point is when it's going fastest. And then as it travels away from the sun, it's going against gravity, so it's going to lose speed until it reaches aphelion again. So throw something up in the air. When it's traveling away from the gravity, it slows down, reaches the top of its path, and eventually falls back towards the Earth and speeds back up. So my analogy was for you throwing something on Earth. Right? Just take that analogy and use it for the planet and the sun. The planet traveling away from the sun's gravity slows down. Falling towards the sun's gravity speeds up. Kepler's third law. Kepler's third law doesn't look at how one planet moves in its orbit. It looks at, aphelion and perihelion, faster and slower. It compares the different planets. Uranus to Neptune, Earth to Mars. So what Kepler's third law says is that the time for one orbit in Earth years, so we're measuring in Earth years. So the time for one orbit. So for Earth, it takes one Earth year to go around the sun once. For Pluto, it's probably, I think, something like 260 Earth years to go around the sun once. So what you would do is you would take the time that that planet goes around in Earth years, and you square it, or multiply it by itself. Okay. And that has to be equal to the length of the semi-major axis if you measure it in AU. And then you cube it, or multiply it by itself, and then do that again. Okay. If this was physics class, we'd have to do a bit more with the units, because a year squared can't equal an AU cubed, but we're not, so let's not worry about it. Okay. So I made this little plot in Excel, and I took from the back of the book, from the appendices, the time for one orbit measured in Earth years for each planet, and I multiplied it by itself, and I plotted it for each planet. All of the inner planets are hidden down here, but they're there. And then from the appendices, I took the semi-major axis from the planet to the sun, and I cubed it, or multiply it by itself 3 times, and plotted it, and they fit on a perfect line. That's Kepler's third law. What you could use Kepler's third law is if it says if you know the time for one orbit, you can figure out what its semi-major axis is. Or if you know its semi-major axis, you can use that to figure out how long it takes for the planet to go around. So if you know one, you can find the other. There's something I should tell you about the semi-major axis that I have forgotten to so far. The semi-major axis, let me go back here. It's the distance from the center of the ellipse, which is just empty space, to the distant edge. That is the average distance between the sun and the planet. So sometimes, let's go here. Sometimes it's closer to the sun than the semi-major axis if the planet was here. But if the planet's over here, it's further away from the sun, longer than the semi-major axis. So the semi-major axis is actually the average. It works out perfectly in calculus. Okay. So we've got Kepler's 3 laws. Orbits travel on ellipses with the sun at one focus. A planet moves faster after it's fallen closer to the sun. And Kepler's 3rd law, there is a relationship between the size of the orbit and how long it takes to go around. Right, we've got Kepler's 3 laws. And he used a heliocentric model, the sun at the center, and ellipses. And his data is perfect. It's great. It explains the sky. It predicts their positions much better and simpler than Ptolemy's. So he takes his ideas out to the world. And the world still chooses to use the geocentric model of Ptolemy. They are not willing to switch. So take a second and appreciate this. We're right in the 1600s pretty much, and they still refuse to believe that the Earth orbits the sun in the 1600s. They've known that the Earth is round since 500 BC, but they won't accept that the Earth moves around the sun, and it's the 1600s. Alright. So, let's move up to Galileo. Galileo used experiments and ideas to try to point out to people that yes, the Earth can move, and that the heavens don't have to be perfect. Alright? So, we're going to go through what Galileo did, and go through his arguments for the sun-centered model and try to argue against the geocentric model. Galileo is trying to move people to believe that the Earth moves around the sun. Okay? Their main arguments, the people who were keeping to the old model, their arguments were that the Earth cannot be moving, or we would leave behind the clouds. The heavens should be perfect and unchanging, and stellar parallax has not been detected. They knew that if the Earth was moving around the sun, that the stellar parallax should exist, and they cannot find it. So Galileo is going to go through all of these. 1, 2, 3, and we're going to go through all of them. So Galileo did some experiments. Some of them he did in real life. Some of them he just argued what would happen. And so in this experiment that I have up here, you put a ball in a bowl and you let the ball roll down and it'll roll back up. And if there was no friction, if everything was ideal, the ball would roll up to the same height before it ran out of energy and came to a stop. Change the shape of the bowl. It should be the same thing. It's going to roll down, gravity's going to give it speed, and then it's going to roll back up, and if there's no friction, it should reach the same height before it runs out of speed. In real life, there is friction. It wouldn't reach the same height, but Galileo was correct. If there was no friction, it should reach the same height. So let's do this. What if you roll it down and just let it go flat forever? If there was no friction, it would roll forever. So Galileo is trying to get at this idea that the Earth cannot be moving or we would leave behind the clouds. Kind of saying an object can move and keep moving unless there's friction. The friction is what stops it. Back in the 1600s, they thought that if you had empty space with no friction and there was a big chunk of rock moving through space, that it would naturally come to a stop. Even if there was no friction, its natural tendency was to come to a stop, and it would. Galileo is trying to argue that your idea of physics is wrong, that things can just move forever. Their natural tendency is just to move at the same speed in a straight line. So if your basic ideas in physics are wrong, maybe you're wrong about some other stuff. Yes, the clouds can keep moving with Earth, right? Earth can keep moving forever. So Galileo was trying to argue that their basic ideas about physics were wrong, but he could also show them that some of their other ideas were wrong. Their ideas that the heavens had to be perfect and unchanging. So they had already discovered and seen some comets, and a comet will appear in the sky, it'll be bright in the sky for maybe a month, and then it'll fade away. So they already knew that there are some things that happen in the sky that are not perfect and unchanging. Comets were very bad omens before we understood what they were. Okay? But Galileo happened to be alive at a great time. The telescope was just invented, and so he was able to use one of the first telescopes to actually look out. And he was able to see sunspots on the sun. He didn't burn his eyes out, he looked at it properly, he projected the image onto a piece of paper. This is a modern image of what we get from a space telescope, but on the sun there are blemishes. The sun is not perfect, and these blemishes move across the sun as the sun rotates. So Galileo could take his telescope and just project an image of the sun onto the piece of paper and say, look, the sun is not perfect. And if you come back in a week, these spots will move. The sun is not unchanging. He looked at the moon, and with a telescope, you really get a feel for the texture of the moon. You can really feel the depth of some of the craters. I'll invite you guys out to telescope night later this semester. It's worth seeing the seeing the moon through a telescope at least once. Galileo had a telescope, but his telescope was not yet good enough to measure stellar parallax. Stellar parallax is really, truly tiny because the stars are so far away, the parallax angle is so small. But when Galileo did look into the stars with his new telescope, he found many more stars than he had ever seen before in his life. So whereas before you might have only been able to see the brighter stars, looking through a telescope now you could see that there were many more stars there than you could see before. So Galileo argued that maybe if there's more stars than we've ever imagined, maybe they're also further away than we ever imagined. And the something that's further away will have less parallax. So Galileo actually correctly argued that the stars were too far away. Parallax was there, but we just couldn't measure it. It's too small. He was correct. Galileo also did some incorrect things, like his explanation of the tides, but he was right in this. So he didn't measure parallax, it's too small, but he argued why it was too small. So Galileo went through and did a lot of things. And he would present this to people, he would show them experiments, show them the telescope, look out at the night sky. And, people still are not going to believe him. There are some other things that he did that are amazing. Here, let me go through two more things that I think are actually even more important or impressive. Galileo observed the 4 Galilean moons of Jupiter. They're the 4 biggest moons of Jupiter. And so he was able to see that Jupiter wasn't just a dot in the sky now, but it was actually a disk. And he saw little stars next to Jupiter, which turned out to be its moons. And night after night after night, he could see that the moons were going around Jupiter, not around Earth, not around the sun. Jupiter had moons that went around Jupiter. So, if anything, this is proof that not everything goes around Earth. This is proof right here that not everything goes around Earth. So Jupiter is right here in this picture. There would have been a sketch of it that I made with my keyboard, right? And the 4 moons of Jupiter. And the 4 moons of Jupiter are going around in ellipses, but we're seeing it edge on. Not face on like you're looking down at the center of a record, but like you tilt the record and you look at the record edge on. And so the moons appear to just kind of move back and forth, even though they're really going around the planet as an ellipse. Another thing Galileo did, which proves that the Earth is not the center of the universe, is he observed the phases of Venus. Let's ignore the right side of the screen here and look at the left side of the screen. The old way, the way that people are still wanting to believe in the 1600s, has the Earth at the center of the universe. The sun goes around the Earth, and Venus has to be between the Earth and the sun while it goes around its little loop. So let's kind of look at that, change our perspective, and move down here, change our perspective. We're from Earth, looking at the sun. From Earth, looking at the sun, Venus has to stay in between the Earth and the sun on this circle. And so you would only ever see a little crescent, because you're almost always behind Venus, so you're almost always going to see the dark side of Venus. So Venus can either be a new phase, which would happen right here, and right here. New Venus, you'd only see the dark side of Venus, or a crescent. Right? So before they had telescopes, they couldn't actually observe the phases of Venus. They could just see it as a dot of light in the sky. Once Galileo got a hold of one of the first telescopes, he looked at Venus, and he saw that Venus had other phases besides a crescent and new. So here's an animation. The sun at the center. Venus goes around faster because it's closer to the sun and Earth. And as Earth looks at Venus, that's our line of sight. And as they orbit, we will see different phases of Venus. Quarter Venus, crescent Venus, new Venus, crescent, quarter, and gibbous. You're never going to see a full Venus perfectly because it's behind the sun, but quarters and gibbuses were not possible at all in the Ptolemaic system, in the old system. And Galileo could see that it had quarters and gibbuses, and he could show that to people. Here, look through this telescope, right there, that dot in the sky, and tell me what phase it is. And he did that, and people didn't believe him. People did not believe him yet. So we've got the data, we've got the ideas, we've got the observations, but the public, I should say the scientific community as a whole, and thus the public, just no, we're going to keep the Ptolemaic system for a long time. We're going to believe that the Earth is the center because we can't feel it. We can't feel it moving. Slowly over time, we were finally convinced. But it took some time to really shift away from the idea that the Earth was the center of the universe.